I am recording all the lectures, by the way. As many as we can. Obviously, when I had to hook up my personal computer, I think what happened is I put my files on my personal computer and forgot to transfer it to my USB drive. Okay, I need a comma. I forgot a comma. -3, comma 8, comma. There we go. This should do it. I should get a nice, neat matrix here. B equals 10, semicolon 20, semicolon 9. Okay. So I've got two vectors defined, and it warned me it does the square brackets not on the other side. Now, what I'm trying to do is get A times X equals B. The trick with matrices, and let's see, where's my, I forgot where I put my marker, so I'll do it like this. A times X equals B. That's why I like my personal marker, because I know it's got ink in it, but I lost it. See if this will work. Okay, A times X equals B. Matrices are not commutative. That you can't, A times B does not equal B times A in matrices. So when you divide, you got to divide. If you're multiplying from the left, you got to divide from the left. If you have this, then if you're multiplying from the right, you have to divide from the right. There we go. If you're multiplying from the right, you got to divide from the right. If you're multiplying from the left, you got to divide from the left. So the way that you'd solve this particular equation is A goes into B, like so. Your backslash, you'd use a backslash instead of a forward slash. And I'm going to make that equal to X. Boom. Okay. So we get this. Let's see. Let's see. A2. A2 equals A transpose. So and B, we're going to transpose B also. So now we've got row vectors. So now X is a row. We're going to find X2. That should equal, I've made basically this equation here. B is a row, X will be a row, so I'm going to get a matrix times a row will give me a row.
So does X2 X times 2?
No, just the name of the variable. X2, X1, X2, X3, X4, etc. Okay. So now if I do B regular divide by A, I should get a dimensions must agree. Okay. Let's see. Let's try B star A. Or I forgot A2. I needed to use A2. X2 equals B2 divided by A2. I just forgot to use the right variables. Okay. Voila. Same. You'll notice the very top. Same answers, just transpose. What's that now? Yes, I can do that. In linear algebra, when you get to matrix methods or linear algebra and stuff, they do it like this. algebra, when they teach you linear algebra, this is the preferred method. Right. That you put a matrix times a column vector equals another column vector. When you're working in linear algebra, the math department that invented linear algebra some 300 years ago, this is how they designed it. So this top, you're multiplying from the left, so you got to divide from the left. In linear algebra, the conventional form is that way. That's convention. The second way, the row vectors, is not conventional. What I just did here is not conventional. The first one is conventional. There we go. Let's get the format compact going on. Okay, now, there's another way to do it. You can reduce the matrix. So I'm going to make a matrix C equals A comma B. By the way, this just joins, well, let's see what C is. C should just be this in 3 columns, and this in the last column. Now, what's wrong here? Oh, for some strange reason, it said it did this. Oh, well, let's not worry about it. Let's try it again. It got rid of, yeah, no, it's there, okay. A is there, so C equals A comma B, so I should be joining the columns together. Did I hit something wrong? It did. I don't know what is going on. Okay. Reduced format. Gaussian elimination. What they teach you in matrix methods, what they teach you in linear algebra. This is the function in Matlab that does it. Reduced row echelon form. That's what it stands for. You're doing reduction, RR, reduction. Just think R, that function RR stuff means you're reducing the matrix. And what it does is it gives you a 4-column matrix. Let's go, what do we say?
That can solve three equations.
Oh, yeah. It can solve zillions of equations. Right, right. The last row.
Like if you have 3 equations with 3 variables,
Oh,
you
yeah.
can use those equations and reduce row. And it solves for each variable? And it would solve for each variable.
Now, you can just keep putting more and more columns here. So if you have this times something equals this times something equals something else, this times something equals a third thing, and so forth, you can just keep going to infinity and beyond. And it reduces it. Obviously, this answer here, the last column of your output, is the same answer as the division, right?
Is that row echelon, that line, is that CR equals RREF?
Right. Let me do help.
CR is just C
A new reduced. C reduced. I choose R. Okay. Help. RREF. So this tells you about reduced row echelon. It's a way of solving matrices. It's just another way of solving matrices. Okay, and of course the help function tells you about what it does and all that stuff. Here's another useful thing. Determinant of A. If the determinant is 0, you can't get a solution. So determinant of A, it's not 0, so you're fine. I'm going to create another matrix. Let's see, D equals bracket 1, 2, 3, colon 4, 5, 6, colon 7, 8, 9.
So A was a matrix, and why is the answer -439?
You'll get into that when you study matrices. when you study linear algebra. Right now, just know if you go det of a matrix, if that equals 0, you can't solve it. It's not 0, so you're fine. Here is an example of a matrix that will give you 0. So here's the matrix. Yeah, what? Yeah. And you get a very tiny number. It doesn't know it's exactly 0. Very, very tiny number. Okay. So there's lots of other stuff in these matrices. Um, lots of matrix. Your book talks about matrix manipulations that you'll learn about when you get more into linear algebra, eigenvalues and things like that. There's a function called eig, and there's a function called spy, which is kind of neat. Let's see. I can't remember the name of it. Sparse. Uh, is it R sparse? Okay. There, that's the one I wanted. Did you mean, okay. Help on that. Help sparse. Basically creating a um, right, just creating a matrix with a whole bunch of of zeros in it. There's a way to create a random matrix. Let me go look at the help center. Oops. Unless magic, you'll get a real. Um, there we go. Let's try magic. So we're going to say, let's see, we've gone up to D. Let's go E equals magic of 100. Just make a big fat matrix. This is going to be a really boring matrix, boring spy command, by the way, because spy is pretty good. Spy is pretty good for really big matrices, and what it says is there's none that are basically it's a solid wall because there's no zeros. Um, that's why I was. Okay, let's do that. That's a good thing to do. You're right. So EYE or let's make E equals. So make a great big identity matrix, in other words. And let's go spy this one. Now we're going to get something that looks figure. There we go. Now, yeah, you only get solids down the diagonal. Everything else is 0.
So where the line, where the 0 would be, it put a dot.
Yes, yes. It gives you white space where there's a 0, non-white where there's something else. So you could take a look and see what it gives you some high-level view of what your matrices look
Well,
like.
that'd be really useful in financial stuff, right? Because you can plot the zeros where you're not getting money or anything like that.
Right, right. Okay. So you could also do Boolean because the Boolean output gives you a matrix with ones and zeros. So if you do some Boolean operation, then spy it, you can see where zeros are and where non-zeros are. It no, it sets it. It's a Boolean true or false. Boolean 1 or 0. Okay, curve fitting. Let's go to that. And I need to define a couple matrices first. 5 comma 10 comma no, it's different values. Yeah, I'm just writing over x basically. So there's my new x and my new y. 15 yeah, comma 33. Okay, we got a couple vectors. We're going to do plot x versus y, and let's see, blue, solid line. No, I don't want any line. Let's see. I forgot how to do it. I'm not going to worry about that. Just plot it like this. I forget all those little codes for plotting, but you don't need it. You can go here. You can select this object, and you can edit, view, property editor. There we go. I'm looking at the property editor of this line. I say, okay, I don't want a line at all. No line, and I want to change my marker. There we go. Change my marker. And now let's close this down. Now, tools, basic fitting. You can do a few things. And let's just do a linear, first of all. So your coefficient, here's the equation. Y equals this. The linear fit gives you the coefficients of that equation. And, well, you can see the figure as soon as you choose, I'll get rid of the linear. As soon as I hit it, I get a line, the linear fit to these data points. You can remove it or you can leave it alone. Right, it generated a legend for you.
Wait, can you put a cubic fit there?
Absolutely, here we go. In fact, we got two of them now. I'll go ahead and show it. So now I've got two fits. And they're overlaying each other. I say, okay, this is confusing. Let's just see one. So get rid of the linear fit. So now we're only seeing the cubic fit. Yes, it does, doesn't it?
Cubic goes like that.
Well, this data, a cubic doesn't have to go like that.
I mean, if you fit it.
Well, it can have an up and down. A cubic can go up and down.
That's what I'm saying, but it's like fitted to that. So.
Right, right. So this is just one. This is
form of the cubic function.
This is away from the cubic function where the cubic's going up and down. This is the smoother part. It looks like an arc. You're right. So you can try fitting. You can try fitting different things. Let's see. Remove the cubic. Put in the quadratic. They say the more parameters you have, you can fit an elephant if you have enough parameters. We need to get the data points for an elephant and see if we can get a 10th order fit to fit the elephant. But anyway, so let's see, 5th degree. Oh, look at this. We've only got 5 data points, so a 5th degree fit's not going to work. It's going to say, can't do it. 4th degree will work. That's an exact fit. If you have 5 data points and you have a constant plus something times x squared plus something times x cubed times something plus something times x to the 4th, you're going to have an exact fit. So cubic is almost an exact fit. Quadratic works pretty well. In fact, quadratic is very nice. Very.
Let's look at it real quick.
Oh, hang on. Let's do this. So cubic, this is what we get for residuals. Quadratic is just x squared. It goes up to the term x squared. Oh, okay, it's got decent residuals too. Residuals tell you the error. So quadratic's pretty good. Almost as good as cubic. So here it is. Here's what it looks like. So you can play around with different fits. I'm going to do something else. We're going to show how to do a exponential fit, like an RC time constant you guys might run into. So I've got to enter data here. I'm going to use t, time instead. Time, and then the pressure, time and pressure value, or yeah, okay. Okay, plot time versus pressure. And I forget all these little codes. So, let's see. Click here. Yeah, I've got the property editor. Let's get rid of the line. Let's make a nice, neat marker. So that's that. The first thing we can do, well, you can do basic fitting. I'm not going to do that first off. The first thing I'm going to do is I'm going to change, let's see, plot area. There we go. X-axis, Y-axis. Make this a little bigger so you can see what's going on. In fact, I'll just fill up the whole thing. Notice the Y scale down here, linear. You can make it logarithmic. Logarithmic scale, you'll have 10 to some powers on the Y-axis. We can also, let's go back to Matlab command window. We can make P2 equals the natural log of P. So we're doing a different way to do the log scale, and then we're going to go plot T versus P2. Now we can do a linear fit to this. If you expect it to be an exponential relationship, now of course you can do this no lines and markers. You have to go look up the codes to tell it what to do, but you can do it from the command line. Now, you'll notice instead of 10 to some power, it just gives you a regular scale on the y-axis. Tools, basic fitting. Let's see what a linear fit looks like to this. And there we go. You can get the coefficients. So here's the coefficients over here. And remember, we scaled e to the, or excuse me, we took the logarithm of P equals P2. Y here is P2, variable P2. The y-axis is variable P2. And I went and I confused myself a little bit. These are coefficients. But they're different. They have a different meaning than what I did. You can here show equations, and you should be able to. Here's the equation on the plot. You can print it on the plot. Residuals, that's just the errors. How far away does this point deviate from the model? When you really get into statistics, residuals are very, very useful. Spline, what that does is it makes a curve that fits all the data points. So you get a nice smooth curve that fits all the data points. So you can see some of the wiggles. Okay.
So that has 0
residuals, right? Residuals are the sum of squares of the deviations from your model to your actual data. That's what residuals are. And residuals are, you get for each data point, you get a residual. Then the mean sum of squares of residuals it's kind of like a standard deviation. It acts a lot like that. Okay, so your book, page 148, has a bunch of other things you can do. You can issue these things from the command lines, which it talks about. The book goes through other functions that does that. Okay. Integration. Let's do that one. Integrals, calculus, all that stuff. I'm going to close this out. So, the example I'm going to use what's this? You guys, how many of you have had calculus? So what is this integral equal to?
ln, which is 1 minus ln of 1.
And natural log of e minus natural log of 1.
So 1 minus
0.
Logarithm of e minus logarithm of 1, which is
1 minus 0.
1. Yeah, the answer should be 1.
Did you follow that, Luke? You know how much easier it is.
We're going to get into symbolic stuff later. Int, there's two functions, diff and int, that take the derivatives and the integral symbolically. What I'm going to show you now is numeric. Oh, first of all, let's x equals exp to the first power. So that's just, well, if I type x, it's 2.7183. So now I'm going to do quad of the function 1 over x I better watch out. I better not use x here. I better go back to a. And I'm going to get rid of x just so I don't have any confusion. There we go. Get rid of it. Quad. Quad is numerical integration. Quadrature, I don't know if you've studied it in calculus. It's a technique of doing numerical integration. There's a few techniques in Matlab, variations on the same theme of doing numerical integration. You put in the function name and whatever you're going to do, 1./x. So I'm integrating 1 over x from 1 to a. And I get 1. Now, let's do a e to the 2 and do the same integral. This time I expect an answer of what? 2. So a is, now a is x e to the 2.5. A is 12.1825. And if I do the integration, I get 2.5.
So does quad mean integration?
Numerical. Quad. It's a numerical technique of integration. Quadrature, it's a quadrature technique you study in calculus of doing a numeric integral. Int and diff are still the symbolic integral and derivatives, integral derivatives. This book just presents the numerical stuff first, which sounds kind of odd, quad, for integration. Okay. It's just the particular technique you do quadrature. Okay. And Wednesday we will talk about differential equations, and that pretty much, you've already seen F0, by the way, where you have a zero finding functions. That is, you have some function, you can't solve it, you can still get a numerical answer, F0. So you've already seen that. That's part of what's remaining in Chapter 5. I will save differential equations for next time. And I might go over F0 or Fmin and things like that. Yeah.
All my differential equations in class.
Yeah, you could.
In differential equation class.
I'll go through like first order, which a lot of you haven't taken calculus yet, so I'll just do simple differential equations. This is a differential equation, actually here, that the derivative of x with respect to, say, some variable time. Wrong. There we go. Let's see. Yeah, that's x is e to the.
X equals.
Right. I'll go through this simple example next time.
You just switch that to something.
Right. So, now, just to wrap up, I think you guys are starting to understand the need to see this, be exposed to it in class here, and then, of course, you're going to have to take it home or go to the kernel and practice it. Use the time you have here to finish up your practices or to do stuff. And I had a question or two over here, so I'll answer questions for the rest of the hour.